So today's lesson is on lesson 5, Law of Conservation of Energy. To start off, we're just going to talk about the basic of what conservation of energy would be including. First of all, in this grade 12, we're basically only going to be focusing on the elastic gravitational potential and the mechanical kinetics. Those are the three that we really will be talking about. There is assumption that all the other ones were we're assuming there's no frictions and things like that unless otherwise stated. But other types of energy could be sound, radiant meaning light, thermal is heat, electrical is when you have electron flow. Chemicals are things like in a chemical reaction waiting to happen. Same thing with nuclear energy. We in general call storing up of energy potential energy. Sometimes we use the word called store energy, so that's interchangeable. Okay, and we would also be talking about energy can be transformed, but the key thing is that the transformation of energy does not change the total energy. So you can transform from one energy to the other, and we call it the law of conservation of energy. So within any system, we're specifically talking about a closed system. Okay. So meaning I'm not adding anything into it. I'm not putting engine force or something like that. If I have a ball and I tossed it, that's a closed system. But as I'm pushing it forward with extra force or something like that, that's not a closed system at all. So within a closed system, there is an assumption that energy is neither created nor destroyed. So that means the total energy remains constant. And this is probably one of the most fundamental principles of physics. And it only applies to things that are fairly big. Well, things that we can observe, like a car moving or a ball that we're tossing. But when we're talking about atomic level, sometimes it doesn't, the Newton's law doesn't explain it anymore. When we get to unit 5, when we're getting into modern physics, we're going to spend more time talking about it. Okay, so the mechanical energy, basically, we would be talking about three main things. I already highlighted that for you. If you want to take the time and read through this is just to prove to you if one object gains and the other one loses some energy, they always convert from one to another. But this is a proof to tell you that the initial total energy will always be equals to the final total energy. Okay, and there is this big assumption is that there is no friction. Okay, we're assuming that we don't have any heat loss in a roller coaster situation. Okay, so kind of just summarizing it up. Okay, whatever the system is, we use the point EA to represent the total energy at point A. Okay, we use EB equals to the total energy at point B. And at every single point, okay, no matter where it is, there is an assumption that EA would equals to EB and would equals to any other point there are in the system. So if I have a roller coaster ride, if this is EA, this is point B, this is point C, and any other point along the system, the total energy is the same. And what counts as a total energy? Okay, so at point A or any other point, there are three things that we will be considering in total. Okay, we would be talking about EK, EG, and EE. So those are the three things that we're going to be talking about. And specifically, basically every time if there is an EK, it's if we have something that's moving, right? Because we know that EK is half mv squared. So if something possesses speed, it does have a kinetic energy. Okay, EG is if anything that is at a height, okay, at a certain height, h, it possesses some stored energy by going against the gravity. So somebody lifted high up, then it has potential gravitation, potential energy. And last one is if I have some sort of spring, and the spring is either stretch or compress, right? Remember we talked about that it could be either way. So if I have some sort of change from the equilibrium position. So if the question has a spring And if there is a spring that is squished, then it does have elastic potential energy. So it depends on, how the question is going. So question 1. The original height of a stone 3 meters above the ground. Calculate the stone's speed when it has fallen and is now 1 meters above the ground. Question like this, I like to draw a picture, okay? I like to call them point A and point B, and depends on where you want it. You can remember how we said the reference point of H is up to you. They tell you that at a height of 3 meters, it was, okay, it didn't tell you the speed, so you're assuming that the speed wasn't moving at the top. And then now it dropped to the height of 1 meter above the ground. So basically ground is your reference point. That's where H equals to 0. And they're asking you what is the speed. Okay, in this question, we are only involving height and velocity, so I'm not going to put elastic energy in it. There's no point for including it in. So the way that you would start off a question is you always have to write the total energy. Okay, EA equals to EB, even if some of it is 0. I know the velocity is 0 at the top. I am not allowed to just say EA is equals to EG at the bottom for point A. Like, I can't just say that. I actually need to say that I know that the system would involve kinetic and potential energy for both sides. And then you go in and you sub in the 0. If some terms cancel, then you're allowed to do that next. So I'm just going to say that the success criteria is you always have to start off your first equation by saying total energy at one point equals total energy at the other point, because that's the law that you're using to start off your equation. I know you know EK is half mv squared, things like that, but you need to, because of the law, that's why I'm allowed to say that, and that's my starting point. And then you go about and you solve the question. Okay, so the first thing I would do is I clearly draw a picture. Point A, point B, and for each of them, I would list H and B. And then I start off with, this equation. Always. You don't have to write the first one if you don't want. EA equals to EB. I always still just write it because that just somehow sits right with me. The next thing you can do is you can sub in your equation. Okay, so I'm going to do substitutions. I know that EK is half mv squared. And I know that EG is equals to mgh. Okay, so I'm going to start doing substitution into the equation. And I'm also going to cancel anything that are 0. Okay, so the easiest thing to do is I cancel first. Velocity is 0 at point A. If velocity is 0, that means EK is 0. So I'm going to cross this off and make it a 0. And that's the only thing I'm allowed to cancel right now. Everything else is either a question mark or a number. So now I'm going to sub in my equation. I know that EG is mgh. I'm going to write out mgh. Equal. Now the third term, EK is half mv squared. And EG is mgh. I don't need you to write A and B on every single letter, but I want you to kind of keep in mind that I'm kind of keeping the left hand side and the right hand side. I'm just going to do this. I'm kind of keeping the left hand side as anything to do with A, and the right hand side with anything to do with the B. So you don't have to write out all the prefix all the time. Okay? All right. So M, I don't have mass. But because I actually have mass in every single term, I can cancel them. Only if they're in every single term. Okay, what I mean by that, if I have something like this, 1,000 equals to mgh plus 1/2 mv squared, I cannot cancel it. Because cancel really means I divide every single term by the same thing. Like if I'm canceling, I'm really dividing everybody by m. And so these two are gone, these two are gone, but this variable is still here. So if they're not in every single term, I'm not allowed to cancel. If I have this, on the other hand, something like that. I have masses, and if I divide everybody by the mass, You see how now I'm allowed to cancel them out. That's what cancel is. Cancel only is allow only if m is in every term, okay? So keep that in mind. If it's a number equal to that, you can't cancel. All right, so going back to the math now. Okay, so because this is m in everything, I can cancel it. So now I'm going to plug in my information. G is 9.8. The height at point A is 3 equals to 1/2. V squared is what I'm looking for. Adding, m is gone, so 9.8 times h, which is 1.0. Now you're solving the equation for V. I'm just going to change color. You don't have to write this out. If you can punch it straight in and get an answer for me, do that, right? Like I would have just do it in one step on my calculator, but just because we're just starting off, I just want to make sure everybody's on board on how to solve it. So I'm just going to multiply out. So I'm going to change color. You don't have to write this down as I said. Like you can do it one step. So I'm just going to expand it out. This is 29.4. I get half V squared adding 9.8 times 10, so 98. Okay, I have V, so that means I need to bring my 98 over, and because this is adding, I have to subtract it. So this becomes 29.4 minus 9. Oh no, sorry, this is 1. So minus 9.8 equals half V squared. So 29.4 minus 9.8, so 19.6 equals half V squared. Multiply the 2 over to the other side, and then take the square root. So the answer I got for V would be 6.2. Please assume 2 sig digs. All right. So, the height of the roller coaster is 40 meters. The roller coaster starts from rest at the top of the hill. Calculate the speed of the roller coaster at the bottom of the hill, and then count at what height will have half the speed in A. So draw your roller coaster. So your roller coaster is 40 meters high. So I'm going to call this point A. The first point I'm going to do with, I'm going to call it point B. And they tell you it's at the bottom of the hill. So at point B, the height is 0. I'm looking for what is the speed at the bottom. And then at point A, it tells me that the height is 40 meters, and then it starts from rest. So V is, you don't have to write V1, just write V. The speed is 0 meters per second. Okay, please start off your question with conservation of energy. So the conservation of energy is that the total energy at point A equals to the total energy at point B. And for the total energy at point A, I have 2 types of energy. I have kinetic energy and gravitational potential energy. At point B, same thing. Total energy at point B would be kinetic energy at point B, adding the gravitational potential at point B. Okay, so now I can go ahead and start deleting things that are 0. So for example, at point A, the velocity is 0, so I know that Vk is 0 because Ek is this part with the speed. And then at the bottom here, it tells you at point B, my h is 0, so this point is also gone. So those 2 terms are gone. So now I'm going to expand out my equation. On the left side, I got Eg, so I know it's mg times h equals to, at the right hand side, I have Ek. The equation for Ek is 1/2 mv squared. I have m and m on each side, so those cancel as well. So now I'm left with g times h equals half v squared. So g times h, which is 40, equals to 1/2. The v is I don't know. Okay, so 9.8 times 40, that equals to 392. Same thing, I'm going to change color. You don't have to write this out. If I were to do this on the calculator, I would go 9.8 times 40 times 2 equal take the square root. The times 2 came from the half, and then the root came from this square, right? So I would have done this on the calculator. Oops. You can times 2 or divide it by half. So I'm just going to multiply this by 2 and then take the root. And that would be what V is. And then as I said, I probably wouldn't even write it out. I would have just gotten straight and get myself an answer. So I got an answer of 28. Okay, the next thing that we need to do now is part B. Part B, I'm going to change the color to a blue color. At what height will it have half of the speed? So for part B, it's going to be point C or any other point, whatever name you want to call it. So I'm going to call it point C, anywhere in here, okay? And it tells me that the speed would be half. So 28 divided by 2, that's 14. And I'm asking for what is the height. So you're allowed to use the values you found at point B or the values that you find at point A. I'm going to still use A because A is the part that is given to me. So I'm going to repeat the question and basically say that EA equals to EC. Because remember we talked about it. The total energy are the same no matter where you are on the point. We're assuming every other point. The billion point, A, B, C, D, E, F, G, wherever the height, wherever the speed is, they all should have the same total energy. So I'm going to start off the question saying EA also equals to EC. And you still need to start with it. EK plus EG equals EK plus EG. You still need to prove to me the conservation of energy. I'm going to give a mark for this. The first one, as I said, you don't have to. Okay? But make sure I write it so that I'm clear knowing that everything on the left-hand side refers to point A. Everything on the right-hand side refers to point C. So I still would like to write it out. Cancel whatever I could. Velocity is still 0. Okay, so expanding this out, I cannot cancel anything on the right-hand side because at point C, I don't have any 0. So MGH equals 1/2 mv squared plus MGH. Cancel out my my mass, because they're in every single term. Expand it out. So now I have 9.8 times the height at 40 equals to 1/2 14 square, adding 9.8 times h. Calculator, I'm going to take 9.8 times 40, and then I'm going to subtract this. This is really a number, right? So minus 0.5 times 14 square equal, and then divide both sides by 9.8. Okay, so I'm going to write it out in a different color. So as I said, you don't have to, right? But I'm just going to show you. So I'm going to move this over by subtracting. So this becomes 9.8 times 40 minus half 14 square equals to 9.8h. So punch that in the calculator if you needed to do it with more than one step, which is okay, right? You need to get it right. If you can bypass this is great, but if you couldn't, getting it correct is more important than your speed. Okay, 294, then I would divide both sides by 9.8, and that's why I would get the height would equals to 30 meters. Okay, and 30 meters has one significant digit, so I am forced to have to put it in scientific notation if I would like to put it in 2 sig. So 3.0 times 10 to the 1 meters. All right, 2 water slider. One that is a track A or B. They're asking you 2 riders start at rest at the same time. Ignore friction, part A. Which rider, A or B, will travel faster at the bottom? So they want you to know what is the velocity for A and the velocity of the B right at the bottom. Okay, based on conservation of energy, the total energies are going to be the same. And at the top, they're all EG. At the bottom, they're all EK, meaning VA and VB should end up with the same speed. So at the bottom, the speed is the same. Okay, part B though. Which rider makes it to the bottom first? What do you think? Okay, part A, you should know how to answer. We did a gizmo, right? Remember you did that experiment, remember? Like, oh, the more steep slope or not as steep slope, if you understand conservation of energy, it is the same. Okay, but A or B, which one get to the bottom first? You write it down. Or you pause the video and you write it down first. Okay, answer? B will reach the bottom first. Because B would spend a longer period of time at a higher speed in comparison to, say, A, spend a lot more time with very, very little speed, right? Because the EK is very small at the top and it stay there for longer. So that's why B would be faster. Okay, so since object on track B will start going at a faster speed, earlier. So we'll spend more time going faster, so it should reach the bottom at faster, but the ending speed is the same for both of them. Okay, so number 4. A dart of mass 1.1 K is pressed against a spring. The spring has a spring constant on 250 and is compressed 6 centimeters and released. If the dart detached from the spring with its normal length, what speed does the dart acquire? Okay, so this is something new. The question 1 and 2 and 3 were from grade 11 when we talk about conservation of energy. Now this is something new. We actually included the elastic energy. Okay, so they tell you the mass is 0.100 kilogram and it's compressed, and they tell you that, so there's two situations again. Okay, the spring constant is 250 newtons per meters, and we have at point A, so situation A is when it is compressed. Okay, so the dart gun is compressed, and then in part B, it is now at normal length. Okay, so can you tell that it's really storing up energy at point A? So I should have EE, some elastic energy that is stored in there. Okay, and then I'm going to know that at this point it's going to be going fast. Okay, so you know how in these questions I would have H and V. So instead of just H and V, we now added an extra parameter. We have H, V, and also X. So for each of the point, you're going to write out what is the height, what is the speed, and what is the X. If it does have V, then it has kinetic energy. Okay, so the height, the dart spring is the same thing. So the height is actually the same for both of them. I'm just going to call them 0 meters. The speed, when it is compressed 6 centimeters, it hasn't moved yet. So there's no speed when it's at point A. But I need to look at what is the speed when it is at point B. At point A, the spring is compressed by 6 centimeters. So please change it to meters divided by 1,000. And then at point B, I don't have any compressions anymore. So X is equals to 0. And now I start off the question exactly the same way as I did. EA equals to EB. The only thing different is now we have added an extra kind of energy on each side. So instead of just EK plus EG, I have EK plus EG plus EE on each side. Pure motion with no elastic, EK and EG. But now when I've added a spring in there, I now add another one. Then the process stays the same. Cancel anything that are a 0. You can't cancel until you write this out. This is 1 mark right here. Okay? So if H is 0, so at point A, so the left-hand side, if H is 0, EG is 0. If V is 0, EK is 0, so I'm only left with EE. On the right-hand side for part B, height is also 0, EG is 0. Velocity is not 0, but then the spring, the compression is 0, so EE is 0. So meaning this equation now will express to this. EE is half kx squared. So the new equation we learned from the last class. EK is 1/2 mv squared. I have half and half. That can go. You can cancel that. All right, the rest you cannot cancel. So let's start plugging them in. K was given is 250. X squared is 0.06 to the square equal to the mass, which is 0.1. And then I'm solving for V squared. So 250 times 0.06 to the square equal divided by 0.1, and then I take the square root, so I get V equals to 3. So please keep how many sig digs? 2 sig digs, 3.0 meters per second. So it's going to be moving that fast. All right, next one. A ball of a mass of 2.6 kilograms start from rest, fall a vertical distance of 55 centimeters before striking a vertical coil spring. The ball comes to a stop when the spring is compressed 15 centimeters, determining the spring constant. Assume the spring has negligible mass. All right, pictures always help. Okay, so I have a mass of 2.0 kilogram. It started from rest and fall 55 centimeters. So fall 55 centimeters. Is it okay if I convert it right away to meters? And that is when it strikes a vertical coil, with an assumption that the coil is not squished. Okay? Then the spring is compressed, so that's the next case. The spring is compressed 15 centimeters, so 0.15 meters. When the ball is right here, it actually stops. Okay? So they're asking you for the spring constant. This is case A, and this is case B. At case A, HVX. At case B, HVX. You do that all the time for every single one. Okay? All right. The most complicated thing with anything vertical is you have to decide your height equals to 0. So it's up to you where you want it, but you have to be consistent. I, in general, like to keep the lowest point of the system to be H equals to 0. I always find that that's just the easiest for me. If you want this point to be H equals to 0, then the height for part B will be negative. Okay, so I just thought it's the easiest if I keep the height being 0 at the bottom. Then look at the picture carefully. What is the height at the top? Okay, if the height is 0 right at the bottom when it's squished, do you see that the height is actually 0.55 plus 0.15? Just look at your picture, right? So this is 0.70 meters at the top. The speed at the top is at rest, so it's 0. At the top, was the spring compressed? No, so the x is 0. At the bottom, it also tells you that the ball comes to a stop when the spring is compressed. So the speed at the bottom is 0. And the spring has compressed by 15 centimeters. So the x is 0.15. Just be careful with your picture that gets you started. So now I have EA equals to EB. I repeat the same process again. What's the total energy at A? Kinetic, potential, and elastic. And then what is the total energy at B? Kinetic, potential, plus elastic. I'm going to say this one last time. You must write this out. If you start this question and you go straight ahead and tell me mgh equals to 1/2 kx squared, you will not get full mark. I will take a mark off because this isn't an equation. I don't know where you got it from. Yes, I know you can assume that I can read your head and I can see your picture. This is the law of conservation of energy. This is an equation that's given. This equation is not given to you. This equation, you work it out based on the situation. Okay? The equation given is the conservation of energy equation. I know total energy equals total energy. That's an equation given. Okay? So I'm going to stress this one more time. I know some of you are going to go straight and tell me mgh equals 1/2 kx squared. And I will mark you wrong. Okay? Make sure you do that. Okay, so let's start canceling. All right, I already told you the next step. Okay, so take a look at point A. Anything that's 0, I cancel. So V is 0, EK is gone. X is 0, EE is gone. On the right-hand side, EB, height is 0, EG. V is 0, EK. So those I can take off. So that's how I got EG is mgh. EE is 1/2 kx squared. Now I plug my things in and I solve it. Okay, so I think you would have everything in there times the height, which is 0.7, equals 1/2 k is what I'm looking for, x squared. So 2.6 times 9.8 times 0.7 times 2 divided by 0.15 squared equal k equals 1585.4 whatever. So sigdics are 3, so I need 3 significant digits, so I'm going to round it to 1590. Oh, what's the unit for k? I'm not going to tell you what's the unit for k. What is it? What is it? What is it? Newtons per meters. Okay? If I can challenge you to stop and do this question on your own before you check my answer, I think that would be great. Okay, Dave jumped off a bridge with a bungee cord tied around his ankle. He falls 15 meters before the bungee cord begins to stretch. Mass is 75. We assume the cord obeys Hooke's law. I don't know if you remember what that means, meaning you can use a K. Okay, K equals, so spring constant is 50 newtons per meters. If we neglect air resistance, estimate how far below the bridge Dave will fall before he comes to a stop. So how far below the bridge will he be before he comes to a stop? Ignore the mass of the cord. If you haven't stopped the video and do this on your own, I really would like you to stop the video and do this on your own. Okay, but now I'm going to take it out because I'm talking to myself. Okay, so if this is the bridge, okay, he falls 15 meters before it starts to stretch. And then it stretch, the spring stretch until he gets to a stop. Okay, it didn't tell you how far it stretched. Let's see what they give you. They gave you this is 15. They gave you K is 50 Newton per meters. They give you the mass is 75 kilograms. And they're telling you that it stops. So at the bottom, when it's stretched to the most, V is equals to 0. That's the only thing you know. I would like you to find how far below the bridge. So they want you to find what is this total distance, okay? What is that? Okay, treat the system as point A and point B, just like what we've been at the top of the bridge, VHX. At the bottom of the bridge, VHX. Okay? All right, so let's see what I have. He started jumping. This is 0. Speed is 0 at the top. The height some of you are going to go straight in and say the height is 15. If you do that, that's okay. But don't forget, if you set that as 15, this is your height at 0. Which is okay. If that's the height of 0, then what you need to do is you need to call the height here something. What's that? What would you call the height here? Okay, so what you need to understand is that there is a stretching. How far did you stretch? You don't know, but you can say I've stretched X amount. Okay, if this is X, if the distance from this point and how far it stretched is X, what is the height? If height is 0 at this point, this height is actually negative X in reference to how far it stretched. So I got my EA and I got my EB. That's one way of doing it. The other ways, if you would like, I don't care which one you use as long as you're correct. If you want, you can always call the lowest point of the system H equals to 0. So I would use X. The stretch is still X. The speed is still 0 at the bottom. But now at the top, speed is still 0. The height would be X plus 15. Do you see that? Like, do you see the picture? X plus 15, that is the total height at the top if I call height equals to 0 at the lowest point. And the X is 0 because at the top, there's no stretching of the spring, so I'm not storing up any energy. I didn't write this down. This is 0. Up to you which one you want to use. You should end up with the same thing. All right, so I'm just going to use the pink one, okay, just because that's what I have. I'm going to leave them here. I'm going to leave them. So I'm going to use the, is it called pink? Or the, I don't know what it is. Purple, pink, magenta, whatever you want. Okay, so I'm just going to use this color, okay? I'm going to say EA equals to EB, okay? What do I start off with? What's the first thing? Yep, your EK plus EG plus EE. The second one is EK plus EG plus EE. First step, always. Okay, now I'm going to cancel anything that are zeros. Take a look at it. Point A on the top, V is 0, EK is gone. X is 0, EE is gone. At the bottom, I'm using the purple, right? Not the purple, I'm using whatever the color is, magenta, okay? At the bottom, speed is 0. I cannot cancel the other two. Okay, so I'm going to plug in what I know. So EG is MGH equals EG, another MGH, and then EE is 1/2 KX squared. Careful, you are not allowed to cancel your M, because this term doesn't have an M. I have people who like to do that. Every time they're so used to canceling the M, then they think they can cancel every time, not when you have a KX squared there. Okay, so I cannot cancel them. All right, now let's start plugging in things I know. Mass times G times the height. Look at your data point, right? I'm using the magenta. So H is 15 equal M G, the H is negative X. Adding, running out of room, 1/2 K, X is X and is X squared. Okay, clean it up. 75 times 9.8 times 15. So I get something like a 11025 equal 75 times 9.8. I'm going to have a negative 735x plus 0.5 times 50. Shouldn't need a calculator. Solve for x. Solve for x. What do I have to do? Okay. Love language. What does it say? Can you read my hand lettering? Yes. It doesn't go away. It doesn't go away. It doesn't go away. I have a number, I have an x, and I have an x squared. Ha! Quadratic. Okay, bring everything to the right hand side, put it in the format of a, b, and c. So I'm going to put it in the format of ax squared plus bx plus c equals to 0. Move everything to the right hand side. I'm going to start off with the 25x squared. The b is negative 735. Move my c by minusing. I get my quadratic. Yes. Okay, so what is x? Minus b, negative b. Okay, we want to write out the equation. Negative b plus or minus b squared minus 4ac. Take the root over 2a. Alright, so minus b is a positive 735. Take the root of 735 squared minus 4ac all divided by 2a. So do the discriminant first. 735 squared. Adding 4 times 25 times 735. Take the root. So I got something like a 783. So, oh, it doesn't look right. I didn't get the right thing. Did I? Oh, it's a C. Oh, sorry, this is C. So minus 11025, made a mistake, sorry. 025, take the root. So this is equals 735 plus or minus 1282 over 50. So I got 40.333, something like that. Okay, so then they're asking you, the other one is a negative number, so I'm not going to care about a negative length. So what is this now? I'm going to erase this. Final question is, they're asking you how far below the bridge. So how far below the bridge? Don't forget that you need to, first of all, it's 15 plus the stretching, which is 40.3. So it worked out to be 55.3. So I'm going to write 55 meters. Okay. Typical test question. You know you're getting this question on the test. And this is probably one of the hardest it can go. Right? Okay. So make sure you do your homework. There is a problem set that goes with this type of questions.